Find the positive integer values for k so that the quadratic equation 2x squared plus 4kx plus brackets 2k squared plus 3k minus 11 bracket equals 0 has real rational solutions, justifying our answer. So real rational solutions, straight off the bat, we should be thinking discriminant, because using the discriminant, it can tell us if, the three cases. So if the discriminant is negative, that means there are no solutions, or no real solutions rather. If the discriminant is equal to 0, there are two identical solutions, or one repeated solution. And if the discriminant is positive, there are two distinct solutions. All right, so we're looking for real and rational solutions. So that could either be the discriminant equals 0 or greater than 0. So we could start with that. So the discriminant must be greater than or equal to 0 for rational, or for real solutions. So that's our starting point. And we do have the quadratic equation up here in standard form. So A would be 2, B would be 4k, and C would be that expression. So we can work out the discriminant. B squared would be 4k all squared. Don't forget the brackets. It's not the same as 4k squared. That is a different expression. Minus 4 times A times C. And C is a quadratic expression itself, which is interesting. Now we can expand and simplify. 16k squared, that's minus 8. We'll just take it in 2 steps so we don't stuff up, because I know I will. Minus 16k squared plus, nope, minus 8 times 3k minus 24k, minus 8 times minus 11 plus 88. 16k squareds cancel. Left with minus 24k plus 88. All right, so we said that the discriminant must be greater than or equal to 0 for there to be real solutions, or at least one real solution, right? It can be 1 or 2. Now we can solve for k. So we'd add 24k on both sides and then divide both sides by 24. So k must be less than or equal to 88 divided by 24. Can we simplify that? I think, yeah, 8 goes into both of those, right? So that's 11 over 3. So let me just write that the conventional way. So k must be less than or equal to 11 over 3. Awesome. So we've found possible values for k so that the quadratic has real solutions, right? But now we need possible positive integer values for k. So just looking at 11 over 3, what is that as a decimal? 11 over 3, 3.667. Okay, so to be positive, k could be 1, 2, or 3, right? It can't be 4, because that's greater than 11 thirds. And it can't be 0 or less, because that would be negative or non-positive. So the possible values for k would be 1, 2, and 3. But that is asking for real and rational solutions. So let's just check each value for k to see what the solutions are and if it meets the the requirement. So just to summarize what we've done so far is to find real solutions, we've set the discriminant to be 0 or greater. We've then calculated the discriminant in terms of k. We then worked out k must be less than or equal to 11 over 3. However, for it to be a positive whole number, k must be 1, 2, or 3. Right, and now what we're going to do is we're just going to check those values of k by putting them into our quadratic equation and finding the solutions. If we had more than 3 values for k, this would be quite tedious, so that would be, you'd be looking at trying to figure a shortcut. But here, since there's only 3, a good approach is actually just trying them all. So we can do that with our calculator. So let me just, what is it? So we have 2x squared plus 4kx plus 2k squared plus 3k minus 11. Equals 0. And so, again, this is our quadratic equation. We've narrowed it down to 3 possible values for k. So k could equal 1. So we'll try that. So when k is 1, our quadratic becomes plus 4x plus 1 squared, that's 2, plus 3 minus 11. So 5 minus 11 is minus 6. Equals 0. For k equals 2, we have 2x squared plus 8x plus, what is that? 2 times k squared, so that's 4, 8 plus 6, which is 14, minus 11, which is 3. And finally, for k equals 3, we have 2x squared plus 12x plus 9, 18 plus 9 minus 11. What is that? 27, 16 equals 0. Right, so we've got our quadratic equations for those 3 possible values for k. And what we can now do is just solve them. But since solving 3, let's not waste our time. Let's just use our calculator. So menu, equate, polynomial, degree 2. So for k equals 1, a is 2, b is 4, c is negative 6. We hit solve. So x, the solutions could be 1 or negative 3. And those are rational. So I forgot to define rational earlier. Rational just means it's either an integer number itself, so like 1, 2, 3, 4, 5, 6, or it's a fraction of 2 integer numbers. Right? An irrational number is a number like the square root of 2, right? Where the decimal goes on forever. It cannot be expressed as a fraction like this of 2 integer numbers. So k equals 1 gives us solutions that are real and rational. So k equals 1 works. Now we can try k equals 2. So that's 2 for A, 8 for B, plus 3 for C. We hit solve. And now here we go. So I know that these are not rational numbers, because if they were, our calculator would have their rational, like their fraction representation here, as long as the numbers aren't ridiculously massive. So I don't even need to write the solutions down, but because I know k equals 2 is not valid, and let's just try k equals 3, 2, 12, and 16. Solve. X equals negative 2 and x equals negative 4. So by substituting in a value for k into the quadratic equation and then solving the 3 quadratics, we can conclude k must be 1 or 3 for the quadratic. So I'll just use a star here for the quadratic to have real rational solutions. Full stop. Another way we could reason about this, so that's a perfectly valid approach, kind of a bit of trial and error at the end there, just testing all our solutions. However, a more elegant way could be to consider the quadratic formula. Right. Just move that down a bit. Come on. Thank you. So for the solution to be rational, B and A are rational in this problem, right? So B is 4k, so k is 1, 2, or 3, so that's always rational. C is always rational, right? We're just squaring the number, timesing it by 2, adding 3 times the number, minusing 11. That's always rational. A is always rational, that's just 2. So the only thing that might not be rational is this square root term. So this b squared minus 4ac is actually the discriminant, right? So if this discriminant is not a perfect square, so it's not 1, 4, 9, 16, 25, so on, then the square root of that will be an irrational number, which we're then adding to b, so that will be an irrational number, which means the overall solution is also irrational. So just checking for k equals 1, right? The discriminant would be 88 minus 24, which is 64, which is a perfect square. So that works. When k equals 2, the discriminant would equal 88 minus 48, which is 40. That is not a perfect square. So k equals 2 does not work. And finally, k equals 3 is 88 minus 72, which equals 16, which again is a perfect square. So k equals 3 is a valid value for k. All right, so that way's a bit nicer to do, but it's a bit harder to pick up on. So I just wanted to show you both strategies. All right, have a wonderful day. Bye.